So today we're going to have a look at how trigonometry can help us solve some real life problems. One of the key terms that they use in problems are either angle of elevation or the angle of depression. So obviously it's very important that we know what they're talking about. Both of these words are given relative to a horizontal line. So if you imagine you're standing looking forward directly horizontally, the angle of elevation is the angle that you have to look up in order to see an object, whereas the angle of depression is from when you're looking horizontally, what angle would you have to look down in order to see the object. So it's really important that you make a little sketch of this diagram now, just so that you know what the two key terms are. So here's our first problem. So we know that trigonometry and Pythagoras' theorem are all about right-angled triangles, but it doesn't mean we can't have two right-angled triangles connected together, in this case forming a quadrilateral. So we are looking for the length CD overall, made up of a full quadrilateral ABCD. So we've obviously got two right-angled triangles, we've got ABD and we've also got BDC. And if we look at that first triangle ABD, we've already got two lengths, so we could quite easily find the third length here by using Pythagoras' theorem. So if we label up that right angled triangle, here's the hypotenuse, and then we can label A and B however we wish. So Pythagoras' theorem says A squared plus B squared is equal to the hypotenuse squared. So A squared here is 12 squared, B squared is unknown, and the hypotenuse squared is 16. So 12 squared is 144. We don't know B squared yet. And 16 squared is 256. Now we know that to get B by itself, we're going to have to do some kind of subtraction, because at the moment 144 is being added. So B squared is therefore 256 minus 144, and that gives us 112. And then we need to find the square root of 112. But as we don't know that answer exactly, we are going to leave that in its surd form rather than getting a decimal and rounding it. So this way we've got an exact value, the square root of 112, which is the length of BD. So now we're ready to have a look at the second triangle in order to find the length CD. So I'm going to call that X because that's the side I'm trying to find. And if I now go ahead and label up my triangle, there's the hypotenuse. Here is the adjacent as it connects the right angle with the angle, and therefore this is the opposite. So I'm going to get the highlighter out to look at what we've got. So I've got to find the hypotenuse, and I know the opposite in surd form. So opposite and hypotenuse, according to the SOHCAHTOA triangles, that means I'm going to use sine. So sine theta is opposite over hypotenuse. So if I'm trying to find the hypotenuse, I imagine putting my thumb over the H, and it tells me that I need to do the opposite over sine theta. So X equals opposite over sine theta. The opposite is the square root of 112 over sine, and the angle is 40. Then we'll grab the calculator. And that comes out as 16.5. The units are centimetres, and we've rounded to 3 significant figures. Okay, so this one's a more practical problem. We've got a homeowner who's trying to construct a ramp up to his front door so that it would be wheelchair accessible. So we've got a door to his home, which is 1.2 metres above ground level, and he wants the angle of elevation to be 20 degrees. So that's probably due to the considerations of somebody having to push the wheelchair up it. We don't want the ramp to be too steep of a gradient, and we're asked to find out what is the length of the ramp. So we're going to have to start off by drawing a diagram of this situation and marking on all the elements that we know, and then we should be able to apply some trigonometry. So here's a fairly basic right-angled triangle. We know that the angle of elevation of the ramp, so from the horizontal here looking up, has to be 20 degrees. And we know that the height change from sort of the ground leading up, here's the ramp, and his door is her door is 1.2 metres up there. Okay, so now we carry on as we normally would do. We've got our angle, and therefore here's the hypotenuse. The adjacent connects the two angles, and 1.2 metres becomes the opposite. So making a note now of what we know and what we're trying to find. We know the opposite, so we're going to find a formula triangle where the opposite is involved, and the length of the ramp is going to be the hypotenuse just here. So opposite and hypotenuse, that tells us we're going to be using sine theta. And we are trying to find the hypotenuse, and therefore the hypotenuse that we'll call x is going to be equal to the opposite over sine theta. That opposite is 1.2 over sine, and the angle is 20. So the full length of the ramp is 3.51 metres, correct to 3 significant figures. And of course in centimetres we'd have to times that by 100, which would be 351 centimetres if it asks for it in those units. So in this final problem, there's an awful lot of information here that we don't necessarily need. Just because something's a number doesn't mean that it's actually going to help us out in the question. So first of all, we know the name of the aircraft is an Airbus A318. That's just the number of the aircraft, so that's not actually useful for us in any way. It's a 100-seater aircraft, probably not going to be using that figure either. It tells us that it has a capability of landing on short runways. It has a steep approach procedure which enables it to land at 5.5 degrees, which is the angle of depression, whereas most aircraft have an angle of approach of 3 degrees angle of depression. We then see that the GPS has advised them that the ground distance, that's our horizontal distance, to the airport is 2 kilometres, so we're asked to find how high he should be above the ground if he's approaching at this 5.5 degree angle. So we're going to need to draw a sketch of the situation. We can imagine that we've got the ground level about here, and we've currently got the aircraft at some height there. So it's going to be coming into land. Obviously not that steeply, but this is just our sketch. We're also going to put the right angle in the corner here. And just do a little bit of labelling. So we're told that the ground distance is 2 kilometres. We're told that the angle of approach is 5.5 degrees. So if we've got our aircraft just up here, remember that the angle of depression is from a horizontal looking down, so at 5.5 degrees. So we could actually form our right angle triangle here instead. So there's our distance of 2 kilometres, and this is going to be the height of the aircraft. So we might actually want to get rid of this part of our diagram in case it confuses us. Okay, so now we've got all the information onto the diagram, it then proceeds exactly the same as every other trigonometry question has. So here's the hypotenuse, the adjacent connects those two angles, and here is the opposite. So we're being asked to find the opposite, the height, and we know the adjacent. So opposite and adjacent, that gives us the tan triangle. So in order to put this together, we're trying to find the opposite, which we're going to call x. So x equals, and if it's opposite that we've covered up, it's telling us to do tan theta times the adjacent. So here we've got tan 5.5 times 2. And that comes out as 0.193 kilometres to 3 significant figures. So due to the size of that, it was less than 1 kilometre, it would be sensible to convert that into metres by timesing by 1000.